Welcome to The Deep Dive, the show dedicated to cutting through the noise and getting you truly well-informed on fascinating topics. Fast.
Glad to be here.
Today, we're plunging into a world where data isn't just big, it's truly gargantuan. I mean, think about it. Every scroll, every click, every streaming binge, it all generates just this overwhelming amount of information.
It really does, and companies are increasingly finding themselves, well, struggling just to keep pace.
Exactly. And while traditional database solutions are, foundational, sometimes they can't scale to the demands of modern web applications.
It's a challenge of scale that, frankly, few could have predicted decades ago, and that's precisely where our focus for this deep dive comes in.
Absolutely. Today, we're taking a deep dive into Apache Cassandra. It's a distributed data storage system that really rose to prominence, solving this exact web-scale problem for tech giants like Facebook, Twitter, and Netflix.
Right, the big players who hit these limits first.
So our mission for you today is to unpack what makes Cassandra fundamentally different from the databases you might be familiar with, why these differences really matter, and how it tackles the incredible demands of modern applications.
You should walk away with a pretty clear understanding of its core concepts, how it operates under the hood, and where it fits into this ever-evolving data landscape.
And to guide us on this journey, our source material for this deep dive is Cassandra, the definitive guide Jeff Carpenter, Eben Hewitt, revised, 3rd edition, which is a truly comprehensive technical guide.
It's a solid resource.
Okay, so let's unpack this. I think we have to start by acknowledging the foundational technology that came before, relational databases. I mean, they've been around for decades.
Oh yeah, the standard.
SQL is widely taught, widely understood, they're feature-rich, and honestly, they make it incredibly easy for junior developers to get started. So what could possibly be wrong with them?
That's a great question. And the short answer, maybe surprisingly, is, well, nothing really. Relational databases, or RDBMSs, that's short for Relational Database Management Systems, they're incredibly successful at solving certain kinds of data storage problems.
Okay.
And SQL, with its simple declarative syntax, is a huge part of that success. Plus, you've got robust tools, easy integration with drivers. They work very well for what they were designed for.
So if relational databases aren't inherently flawed, what was the real tipping point? What demanded something new?
Well, the nothing is wrong part applies, within their design constraints. The problems really start to emerge when relational applications become too successful and usage just scales up massively.
Ah, okay. Success becomes the problem.
Kind of, yeah. Think about how they're designed. To gather related data, you often use joins across multiple tables, right? That's central to the relational model.
Sure, normalization.
Exactly. But under really heavy loads, those joins can become incredibly slow, a real bottleneck.
So the very architectural strength joining data becomes a weakness at web scale. What about handling individual changes, like transactions? Is it a similar story there?
Precisely. And that's why ACD properties come in atomicity, consistency, isolation, durability. These are great for ensuring data consistency.
The gold standard, really.
But they typically require locking portions of the database. So what happens under very heavy loads, users start queuing up, basically waiting for their turn to read or write data. It just becomes a major bottleneck.
Right. And the usual fix for that, at least initially, is just to throw more hardware at it, right? More RAM, faster CPUs, vertical scaling.
Yeah, vertical scaling, that's often the first step, get a bigger box, but it's really just a temporary fix. Eventually that one box maxes out.
And then you're stuck.
Then you're faced with horizontal scaling, adding more machines to your cluster. And that's where a whole new set of problems crop up, like how do you manage data replication and consistency across all those new boxes, especially if one fails?
Right. Failover scenarios get complicated fast. So developers try workarounds, almost like patching the system. I've heard of denormalizing data.
Oh, yeah.
Which feels totally wrong if you come from a relational background.
Or moving processing into the application layer itself.
Yes, those are really common compensatory actions.
Yeah.
Denormalizing data, like you said, it fundamentally disrupts that elegant relational design, moving processing to the application layer that often just shifts the bottleneck around without truly solving it.
And caching. Adding layers like Redis or memcached.
Caching is another big one.
Yeah.
But then you introduce a whole new headache, keeping the cache consistent with the database itself. That's a notoriously tricky problem.
So it really boils down to this. The limitations of RDBMSs, especially when distributed transactions become this severe bottleneck, just made it clear that new solutions were needed. NoSQL then wasn't maybe so much a radical departure as almost a natural evolution. That's an excellent way to put it. It really encapsulates work that was already being done to manage these very large databases, but with architectures specifically designed to handle the web's phenomenal growth and that need for near real-time data processing.
Okay, so with that context, what's Cassandra's elevator pitch? How does it tackle these problems differently?
Well, at its core, Cassandra is a free, open-source, distributed data storage system. It runs on multiple machines, but it acts as a unified whole.
Okay, distributed.
And crucially, it's decentralized. There's no single point of failure, which enables really high availability. The source material actually notes there's a little point in running a single Cassandra node to get the real benefits.
Right, it's built for the cluster.
Exactly. Its design is engineered for distributed performance, even across multiple data centers. You can write data anywhere in the cluster, and Cassandra makes sure it gets to the right places.
Okay, that's the distributed and decentralized part. What about scaling? How does it handle that massive growth we talked about?
That leads directly to elastic scalability. So unlike vertical scaling, getting a bare box, Cassandra is designed from the ground up for horizontal scaling.
Adding more boxes.
Yep. You simply add more machines, often just commodity hardware to bear the load, and the system seamlessly incorporates them. It does this without sacrificing performance, even scaling up to hundreds of terabytes under heavy load.
So high availability and fault tolerance are kind of a natural outcome of that decentralized design. If one node goes down, the system keeps running.
Correct. The loss of a node doesn't bring the whole system down.
But when we talk about NoSQL, consistency often comes up. It's a key difference, right? Many systems are labeled eventually consistent. How does Cassandra approach that? It's pretty crucial.
It is crucial, and that's actually a common misconception about Cassandra. It's not just eventually consistent. It's more accurately termed tunably consistent.
Tunably consistent. Okay, what does that mean?
It means you, the developer or operator, get to easily decide the level of consistency you require for a given operation, balancing it against availability. And this connects directly to Brewer's KP theorem.
Ah, the CP theorem. Right. Consistency, availability, and partition tolerance. Pick two.
Exactly. The classic trade-off. If you choose CP, consistency, and partition tolerance, you get consistent data even if the network splits, but you risk unavailability if a node involved fails.
Okay.
If you choose AP availability and partition tolerance, your system is always available, even with network partitioning, but it might return slightly stale or inaccurate data temporarily. DNS is often cited as a popular example of an AP system.
So where does Cassandra fit?
Out of the box, Cassandra generally leans towards availability and partition tolerance, AP. But the real beauty is that you can choose your consistency level per query. You can dynamically trade off for stronger consistency when an operation absolutely demands it.
Wow, okay, so unlike traditional databases that kind of force you into one strict consistency model, Cassandra gives you a literal dial you can turn.
Pretty much, yeah.
So you could design, say, a global app where maybe user profiles can be eventually consistent for speed, but something like a financial transaction needs immediate ironclad accuracy. That level of granular control sounds like a game changer.
Exactly. It's about giving you the power to make the right trade-off for your specific use case, not a one-size-fits-all approach.
Okay, that makes sense. And what about schema? Relational databases are all about strict schemas defined upfront. Cassandra was initially called schema-free, then maybe schema-optional. What's the reality now? How flexible is it really?
That's evolved too. I think the best way to describe Cassandra's current approach is that it supports a flexible schema. The Cassandra query language, CQL, brought in SQL-like schema definition, which feels familiar.
Okay.
And with the 4.0 release, the old, truly schema-free Thrift API was entirely removed. So the storage engine is now fully aligned with CQL.
But there's still flexibility.
Yes, definitely. CQL collections, things like lists, sets, and maps, along with JSON support, still provide a lot of flexibility. You can evolve your data model without needing that rigid upfront definition for every single thing.
So super scalable, highly available, tunably consistent, and flexible on schema. It's quite a compelling package. But for someone like me, steeped in relational thinking, I imagine the way you actually model data in Cassandra must be, well, a completely different animal. requires a real shift in mindset.
It absolutely is a mind bender initially, no doubt about it. Even some familiar terms like column exist in both worlds but have very different meanings in Cassandra.
Okay, so what's the structure?
In Cassandra, you have this hierarchy. At the top, you have clusters, then key spaces, which are roughly similar to relational databases or schemas. Then you have tables. These used to be called column families back in the day.
Right, I remember that term.
Within tables, you define partition keys and clustering columns. Together, those form the primary key. That primary key defines your rows, and rows then contain individual columns.
And a huge difference I've heard about is denormalization. In relational databases, you fight tooth and nail to avoid it because it violates COD's normal forms. But in Cassandra,
In Cassandra, denormalization is, well, perfectly normal. It's often not just allowed, but actually necessary for performance. It's really a key design principle.
so you duplicate data intentionally.
Yes. Historically, that meant manually managing multiple tables to keep things in sync. But since the 3.0 release, Cassandra has offered an experimental feature called materialized views for server-side denormalization. Cassandra manages the syncing for you in that case.
Okay, that sounds helpful. Are there other ways?
There are also secondary indexes. But it's important to know that queries using secondary indexes often involve hitting more nodes in the cluster, so they might not scale as well as queries based directly on the primary key. It's a trade-off.
So the core idea then is this query-first design. You don't just model the data structure itself, you model how you're going to ask for it. That seems like the biggest shift from relational.
Precisely. That's the fundamental difference. You design your data model around your anticipated queries. Let's
Yeah.
take a hotel application example.
Right.
If you don't foresee any queries that need direct access to, say, room details or amenity details as separate things, you wouldn't necessarily create dedicated tables for rooms or amenities, unlike how you probably would in a standard relational design.
Right, you just embed that info where you need it for the queries you do have.
Yeah.
So denormalization is normal. How does that translate to the physical way Cassandra organizes data? And what about partition size? You mentioned partition keys.
Yeah, that's crucial. Cassandra distributes data across the cluster, the ring, based on the hash of your partition key. Each partition, which contains all the rows for that key, lives on a specific set of nodes determined by the replication strategy.
Okay.
And understanding partition size is absolutely vital because it directly impacts performance. If you put too much data into a single partition, you can create hotspots, performance issues, even memory problems on the nodes holding that partition.
So you want to spread the data out evenly using the partition key.
Exactly. There are formulas to estimate partition size, but the key takeaway is design your partition keys carefully to distribute data evenly and avoid creating these massive superpartitions that become bottlenecks.
Got it. Let's talk about SQL well syntax for a minute because, it looks familiar, but you mentioned some crucial differences. We've got create key space, create table, insert, select, delete. That all seems pretty standard.
Yes, the basics look familiar, which helps with adoption, but a key difference is with insert and update. In Cassandra, they exhibit what's called upsert behavior.
Upsert, like update or insert.
Exactly. Because Cassandra uses an append-only model internally for writes, there's no fundamental difference between an insert and an update operation from its perspective. If you insert a row with a primary key that already exists, Cassandra just replaces the existing row with the new data.
And if you update a row that doesn't exist,
Cassandra just creates it. So insert and update essentially merge into one upsert operation.
interesting. And there's this powerful feature called time to live, or TTL. I love the sound of that, setting data to just disappear.
TTL is fantastic, yeah. It allows you to automatically expire data, and you can do it at the individual column level, which is really granular. It helps manage the data lifecycle without needing manual delete jobs. You can set a specific duration or set it to null if you want the data to stick around indefinitely.
Data types seem pretty flexible too, going beyond just basic text and numbers.
Absolutely. CQL supports a wide range of types. You've got numeric types, textual types, but also time and identity types like timestamp, date, time, and UID.
UIDs are those unique identifiers, right?
Yep, universally unique identifiers. They're 128-bit values, often based on random numbers or time plus machine info, great for generating unique primary keys across a distributed system. And CQL also supports collections list, set, map, and even user-defined types, or UDTs, where you can create your own custom data structures.
And Cassandra tries to be helpful, right? It warns you if you're about to do something potentially inefficient, like with that allow filtering clause.
Yes, exactly. If you try to run a select query that filters on a column that isn't part of your partition key or clustering key, Cassandra knows this might require scanning a lot of data across many nodes, which doesn't scale well.
So it makes you explicitly say, yes, I know this might be slow.
Precisely. It will give you a warning and require you to add allow filtering to the query. It's really trying to encourage you to design your queries and your data model to avoid those full table scans or large partition scans, which can be very expensive in a distributed system. It's Cassandra's way of saying, are you sure you want to do this? It might hurt later when you have more data.
Okay, so that's the data model and how we interact with it via SQL. Now let's pull back the curtain a bit further. How does Cassandra actually work under the hood? What's its architecture like?
Okay, so the foundation is its cluster topology. Cassandra is designed to be aware of where your nodes physically are in which data centers and which racks within those data centers.
Why is that important?
It uses this information to store data replicas smartly and route queries efficiently. It places copies of your data in the data centers you specify to maximize availability and tolerance to network partitions, but it also tries to route queries to nodes in the local data center whenever possible for better performance.
And how do all these nodes coordinate? How do they share this topology information and know who's up or down? Is there a central coordinator?
No central coordinator that's key to its fault tolerance. They use something really fascinating called the gossip protocol.
Gossip, like they're chatting with each other.
Kind of, yeah. Think of it like a peer-to-peer group chat. Each node periodically whispers small updates about itself and others it knows about to a few random neighbors. Those neighbors then pass the information along.
Okay.
This decentralized chatter allows the entire cluster to quickly converge on a shared understanding of who's up, who's down, what load they have, and what version they're running, all without needing a single boss node telling everyone what's going on.
So that's how it detects failures too, through gossip. Is it just a simple, this node isn't responding kind of thing?
It's a bit more sophisticated than that. Cassandra uses something called the fiocrul failure detector. This came out of research in Japan back in 2004.
Fiocrul. Okay.
Instead of just a binary dead or alive state, which can be flaky in real-world networks, it calculates a suspicion level, the phi value for each node. This value represents the probability that a node is actually down.
So it adapts to network conditions.
Exactly. It adapts to things like network latency and jitter, making Cassandra's failure detection much more robust and less prone to declaring a node dead just because of a temporary network blip.
Okay, gossip handles state. What about routing queries efficiently? You mentioned snitches earlier. What an interesting name. What do they do?
Yeah, snitches. They provide that network topology information to Cassandra, telling it about the layout of racks and data centers. This allows the coordinator node for a query to route requests efficiently. They help determine the relative proximity of different nodes and identify the fastest replica to read from, which is crucial for low latency reads. The default, simple snitch, isn't topology aware, so for any real multi-rack or multi-data center setup, you'd use something like gossiping property file snitch.
Why that one?
Because with gossiping property file snitch, the nodes actually exchange their rack and data center locations via the gossip protocol itself, so the topology information spreads automatically.
Makes sense. So data is conceptually spread across a ring. How does Cassandra decide where on the ring a piece of data goes? And what are these virtual nodes I hear about?
Right, the ring concept. Data is conceptually represented as a ring, usually based on a range of hash values. Each node in the cluster is assigned responsibility for one or more token ranges on this ring.
Tokens?
Yeah, these tokens are typically 64-bit integer IDs that represent partitions. A partitioner, which is basically a hash function, computes the token for a given partition key. That token determines which node, or nodes depending on replication, is responsible for storing that data.
And which partitioner does Cassandra use?
The default since Cassandra 1.2 has been the Murmur 3 partitioner. It's generally very efficient and does a good job of spreading keys evenly across the ring. One critical point, though. You cannot change the partitioner after you initialize a cluster. It's a one-time decision.
Okay, choose wisely. Now, virtual nodes, or vNodes.
vNodes significantly simplify cluster management. Instead of a single node being responsible for one large, contiguous chunk of the token range.
Like one big slice of the pie.
Exactly. With nodes, enabled by default in modern Cassandra, a single physical node owns many smaller, non-contiguous token ranges scattered around the ring.
Boy, is that better.
It spreads the data load much more evenly across the cluster from the start, and it makes operations like bootstrapping new nodes, decommissioning old ones, or repairing nodes much easier and faster because the load gets rebalanced more smoothly across the remaining nodes. It avoids those massive data movements you'd have with single token nodes.
Okay, that makes sense. We talked about replication earlier, conceptually. How does Cassandra actually handle placing those copies across the cluster? What are the strategies?
Cassandra uses replication strategies to determine where to place the replicas copies of your data. The simplest is simple strategy. It just places replicas on the next consecutive nodes around the ring after the primary owner.
But that's not good for fault tolerance across racks or data centers, right?
Right. It's really only suitable for single data center test setups. For production, you absolutely want to use network topology strategy
Why network topology strategy?
because it's topology aware. It allows you to specify a different replication factor for each data center in your cluster. And within a data center, it tries intelligently to place replicas on nodes in different racks, maximizing availability if an entire rack fails.
Got it. And just to hammer this home, because I know it can be confusing, can you quickly restate the difference between the replication factor and the consistency level?
Absolutely. It's a common point of confusion. The replication factor is something you configure per key space in your schema. It dictates how many total copies of each piece of data Cassandra will maintain across the cluster based on your network topology strategy settings.
Okay, so that's about how many copies exist.
Exactly. The consistency level, on the other hand, is something the client specifies per query, per read or write operation. It determines how many of those replicas must respond successfully for that specific operation to be considered successful by the coordinator node.
So that's about how many copies need to agree for my operation.
Precisely. The consistency level is based on the replication factor for that key space, not the total number of nodes in the cluster. So replication factor, how many copies total. Consistency level, how many must acknowledge this specific request.
Perfect. Okay, so you mentioned earlier that Cassandra doesn't have full AC transactions like relational databases, but it does have something called lightweight transactions. How do those work? What's the magic behind them that gives you some level of transactionality?
Right. While Cassandra avoids the complexity and potential bottlenecks of full distributed ACID transactions, lightweight transactions, or LWTs, introduced back in version 2.0, provide transactional behavior for specific common use cases where you need atomicity and isolation for a single operation.
Like what kind of use cases?
The classic one is ensuring uniqueness. Using if not exists on an insert statement guarantees that you won't overwrite an existing row if you're trying to, say, create a unique user account or claim a unique reservation ID.
Okay, like a check and set operation.
Exactly. Or you can use if exists or if column value for conditional updates. Only update this row if this condition is currently true.
So how does it achieve that consistency across nodes?
Under the hood, LWTs use a variation of the Paxos consensus algorithm. It's a well-known, though fairly complex, distributed consensus protocol. It essentially forces the involved replica nodes to go through a rigorous negotiation process, usually involving a two-phase prepare promise and propose accept sequence to ensure they all agree on the single outcome of the operation before it's committed.
So it's heavier than a normal write.
Yes, LWTs incur more network round trips and have higher latency than standard Cassandra reads or writes because of that consensus process. You use them when you absolutely need that guarantee for a specific operation, not for every write, and they require specific consistency levels like serial or local serial.
Okay. What about batches? I sometimes hear those mentioned in relation to transactions. Are they the same thing? Do they give you that all or nothing guarantee across multiple statements?
That's another common point of confusion. Cassandra's batches allow you to group multiple modification statements, insert, update, or delete together into a single request. The main benefit is reducing network overhead by sending them all at once.
But they aren't atomic in the same way as a relational transaction.
Crucially, no. Batches in Cassandra are not a general transaction mechanism providing ACID guarantees across multiple partitions. While Cassandra guarantees that if the statements in a batch are valid, the coordinator will eventually ensure they all get executed, using mechanisms like hinted handoff if nodes are down. They don't provide atomicity in the sense that either all succeed or all fail together across different partitions.
So when should you use batches?
They are primarily useful for two things: making multiple updates to rows within the same partition, because that usually X the same replica set, or for keeping denormalized tables in sync efficiently. Using batches for updates across multiple partitions just to achieve atomicity is generally considered an anti-pattern in Cassandra. LWTs are for single partition atomicity.
Got it. So when I do write data, whether it's a normal write or part of a batch, what's actually happening on the node, how does Cassandra ensure durability? And how does it organize the data on disk for later retrieval?
Think of a standard write in Cassandra as a two-stage process for durability and performance. First, the data is appended to the commit log on disk.
The commit log.
Yeah, it's like a crash-safe, durable journal. Writing sequentially to the commit log is very fast. Once the data is in the commit log, Cassandra acknowledges the write back to the client. It's considered durable at that point, safe even if the server crashes immediately after.
Okay, so commit log first for safety. Then what?
Almost simultaneously, the data is also written to an in-memory data structure called a mem table. This is where recent writes are held and sorted in memory.
And when does it actually hit the main data files on disk?
When that mem table gets full, based on size thresholds, or after a certain time, its entire sorted contents are flushed to disk as a new, immutable S table that stands for sorted string table. These SS tables are the primary on-disk storage format.
Immutable, so they never change once written.
Correct. New data goes into new SS tables. Updates or deletes of existing data also result in new entries in newer SS tables, marking the old data as superseded or deleted.
And what's inside an SS table file? Is it just the raw data?
An SS table is actually typically composed of several files. There's the data.db file containing the actual row data, sorted by primary key. But there are also important companion files, like a filter.db file, which often contains a Bloom filter.
Ah, blue filters again. We mentioned those for speeding things up.
Exactly. And there's usually an index.db file, which contains a sparse index mapping partition keys to offsets within the data.db file, helping Cassandra quickly locate where a partition starts without scanning the whole data file.
Tell me more about those Bloom filters. How do they help reads?
Bloom filters, named after Burton Bloom, who invented them in the 70s, are really clever probabilistic data structures. They are extremely space-efficient ways to quickly check if an element might be present in a set, in this case, if a specific row key might be present in this particular SS table file.
MOB. So they aren't always accurate.
They can produce false positives, meaning the filter might say the data could be there when it actually isn't. But, crucially, they never produce false negatives. If the Bloom filter says the key is definitely not in this SS table, Cassandra can safely skip reading that file entirely.
Ah, so they avoid unnecessary slow disk I/O.
Exactly. Since checking the Bloom filter, which is usually loaded into memory, is much, much faster than hitting the disk, they significantly boost read performance by quickly eliminating SS tables that couldn't possibly contain the requested data. It's like having a very fast, slightly forgetful bouncer at the door of each file.
Okay, that makes sense. And because these SS tables are immutable and you just keep writing new ones, how does Cassandra manage all that? Doesn't the disk fill up with old, superseded, or deleted data?
It would, yes, if not for a critical background process called compaction. Compaction is essential. It periodically reads multiple existing SS tables, merges their data together, reconciles different versions of rows, keeping only the latest, discards data that's older than its TTL, and crucially, discards data marked by tombstones for deletion. It then writes out new, more compact SS tables containing only the live data.
Okay, so compaction cleans things up. What are tombstones? You mentioned deletes are handled differently.
Right. Because SS tables are immutable, Cassandra can't just go back and remove data from an old file when you issue a delete command. Instead, it performs a soft delete by writing a special marker called a tombstone for that specific row or column in a new S table.
So the data's still there, just marked as dead, like leaving a little ghost in the system.
Exactly. That's a good analogy. The tombstone essentially says, ignore any data for this key with a timestamp older than this tombstone. During reads, Cassandra sees the tombstone and knows not to return the older deleted data.
And compaction eventually removes the tombstone and the old data.
Yes, but not immediately. Cassandra waits for a configurable period called Gitu gray seconds, garbage collection gray seconds, before a tombstone is eligible to be permanently removed during compaction, along with the data it marks as deleted.
Wait. Why not clean it up right away?
The grace period is there to give any temporarily downed nodes enough time to recover and receive the tombstone via gossip or read repair. If you remove the tombstone too quickly, a node coming back online might miss the delete and reintroduce the old deleted data back into the cluster.
Consistency across replicas again?
Yeah.
But having lots of tombstones sounds like it could slow down reads, right? Cassandra still has to sift through them.
Absolutely. That's a crucial point for performance tuning. If you have workloads with very frequent overwrites or deletes, you can accumulate a lot of tombstones. Reads then have to process both the live data and potentially many tombstones for the same partition, which can significantly impact read latency. Managing tombstones effectively through data modeling and compaction strategy choices is key. It feels counterintuitive coming from relational, where delete means gone.
Okay, so how does Cassandra optimize the read path, then pulling all this together. It sounds like it might need to check the mem table, potentially multiple SS tables, consult Bloom filters, deal with tombstones.
The read path is indeed quite involved but highly optimized. When a coordinator receives a read request, it figures out which nodes hold the replicas for that data. Depending on the consistency level, it sends requests, potentially just digest requests initially to check for differences, to one or more replicas.
Yeah, man.
On each replica node, Cassandra first checks the mem table for the most recent version of the data. If not found, or if older versions might exist on disk, it then checks the Bloom filters for relevant S-tables. If a Bloom filter indicates a potential match, Cassandra uses the SS table index to find the approximate location on disk, reads the relevant data blocks, potentially merges data from multiple SS tables, if the row spans several, reconciles tombstones, and finally returns the result.
And he uses caches too, right?
Yes, heavily. Key caches store mappings from partition keys to row index entries. Row caches can store entire hot rows in memory. And modern Cassandra uses an off-heap chunk cache for uncompressed SS-stable data blocks. All these layers work together to minimize expensive disk I/O and serve reads as quickly as possible. There's also a process called read repair that can happen in the background or foreground to fix inconsistencies between replicas discovered during a read.
Got it. And I heard there's a relatively new feature in Cassandra 4.0 related to replication, something called transient replication. What's that about?
Yes, transient replication is an interesting experimental feature introduced in 4.0, aimed primarily at very large clusters. It allows you to configure some replicas for a key space as transient.
Transient replicas.
Yeah. Unlike normal full replicas that always store a copy of the data, transient replicas only store the data temporarily when one or more of the full replicas for that data range are unavailable.
What's the benefit of that?
The main goal is to save significant disk storage space as well as reduce the CPU and I/O load associated with compaction and other background tasks on those transient nodes, while still achieving the same high level of availability and consistency guarantees for client requests. It's like having backup replicas that only hold data when needed, reducing the overall resource footprint.
Interesting. Okay, so we've covered the what and the why, the architecture, the data model. Now let's get practical. If someone listening wants to get started with Cassandra, maybe just play around with it locally, how easy is it to just kick the tires?
It's actually surprisingly easy to get a single Cassandra node up and running locally with its default configuration. You basically just download the latest Apache distribution, decompress it, navigate to the bin directory, and start the server.
And how do you interact with it?
You use CQLsh, which is the command line shell for executing CQL commands. It connects automatically to the local node if it's running. So getting a feel for basic CQL and data modeling is pretty straightforward on your own machine.
Okay, that's for local testing. What about for Cassandra cluster? Is it just sending raw CQL strings over the wire?
While there is a native protocol, you almost always use one of the official client drivers. Cassandra has a robust ecosystem of drivers available for most popular programming languages: Java, Python, C#, Node.js, Go, Ruby, C++, Maya, PHP.
And these drivers offer more than just basic connectivity.
Oh yeah, much more. They handle complex things like connection pooling, discovering nodes in the cluster automatically, topology awareness, load balancing requests across nodes intelligently, token awareness, automatic reconnection if a node goes down, handling authentication, and providing higher-level APIs beyond just raw CQL execution. The DataStax Java driver is often considered the reference implementation and is particularly popular, often getting new features first.
Can you tell us a bit more about that Java driver? What makes it powerful for developers?
Sure. The DataStax Java driver provides a really nice, modern, Fluent-style API. The CQL session object is your main entry point for connecting to the cluster. You can execute simple ad hoc queries using simple statements.
Okay.
But for queries you run repeatedly, which is common in applications, you'd use prepared statements. You prepare the query structure once, Cassandra parses and caches it, and then you just execute it multiple times by binding different variable values. This is much more efficient.
That sounds familiar from relational drivers.
It is. The driver also provides a query builder API for constructing CQL queries programmatically in Java, which can be less error-prone than string manipulation. And there's even an object mapper component that can automatically map your Java domain objects, POJOs, to Cassandra tables and back, abstracting away a lot of the boilerplate CQL interaction if you like that style of development.
So the driver handles a lot of the plumbing. And how do you configure it for a real application? Things like which nodes to connect to, authentication, etc.
Right. Typically, you externalize the configuration. You provide the driver with initial contact points, IP addresses or host names of a few nodes in the cluster, the name of the local data center, which helps the load balancing policy prioritize local nodes, and any necessary authentication credentials.
And the driver figures out the rest.
Mostly, yes. It connects to the initial contact points, discovers the rest of the nodes and their topology using system tables, and then manages the connection pool. It has sophisticated policies you can tune, like the load balancing policy, the ATC inferring load balancing policy is common, a reconnection policy to transparently handle nodes going down and coming back up, and connection pooling settings. Interestingly, the default pool size per node is often just one connection now because the protocol is fully asynchronous, allowing many requests in flight simultaneously over that single connection.
I've also heard of something called Stargate recently. What's its role in the ecosystem? Is it an alternative to the drivers?
Stargate is an interesting project. It's an open source data gateway that sits on top of Cassandra, or DSE, DataStax Enterprise. It essentially provides alternative APIs for interacting with your Cassandra data, specifically REST, gRPC, a document API like MongoDB, and GraphQL APIs.
So why would you use Stargate instead of a standard driver?
It can simplify development, especially for teams less familiar with CQL or Cassandra's specific data modeling nuances. It abstracts some of that away. It's also particularly useful if you're working in a language where maybe there isn't a mature, actively maintained Cassandra driver, or if your architecture heavily favors one of those API styles like REST or GraphQL already. It gives you more options for integration.
Okay, cool. Now, shifting gears to actually deploying and configuring a full cluster, what's the main configuration file operators need to worry about?
The primary configuration file is definitely cassandra.yaml. It lives in the conf directory of your Cassandra installation. This is where you define all the critical settings for a node.
Like what kind of settings?
Key things include the cluster name, which must be identical across all nodes in the same cluster, the partitioner, which remember you can't change later, the snitch, which tells Cassandra about the network topology, the listen address, and IRC address, and importantly, the list of seed nodes.
Seed nodes, what are they for?
Seed nodes are the contact points for new nodes joining the cluster. When a node starts up, it contacts the seed nodes to learn about the topology and state of the rest of the cluster via gossip. You need a small, consistent list of seed nodes across your entire cluster. They're kind of like the initial introducers for the gossip protocol.
Got it. And for learning and practicing setting up multi-node clusters, is there an easier way than provisioning multiple VMs or machines? Something for local development.
Absolutely. There's an excellent Python tool called Cassandra Cluster Manager, or CCME. It makes it incredibly easy to create, manage, and destroy multi-node Cassandra clusters right there on your local machine, like your laptop. It handles setting up the different ports, directories, and configurations for each node instance. It's perfect for learning, testing different configurations, or developing applications against a realistic cluster environment without needing lots of hardware.
That sounds super useful. When you do deploy a real production cluster, what are the common deployment scenarios people use these days? Is it mostly cloud?
You see a wide range. Public cloud deployments on AWS, Google Cloud, GCC, and Azure are extremely common, leveraging their infrastructure. But you also see hybrid cloud setups, where a cluster might span both a public cloud and a company's private data center, perhaps for burst capacity or keeping sensitive data on-prem.
And even multiple clouds.
Yes, multi-cloud deployments are also a thing, maybe spanning AWS and GCP, for example. This might be done to locate data closer to users in different regions served by different clouds, or to leverage specific services from each provider, or just for provider redundancy. And within a physical data center or cloud region, it's also common to use logical data centers in Cassandra configuration for workload isolation, like separating transactional workloads from analytics workloads, even if they're running on the same physical hardware.
When you're planning that deployment, how do you figure out how big the cluster needs to be? Especially sizing the disk storage. Is there a rule of thumb?
Sizing is definitely critical planning work. For disk storage, you can estimate the total physical disk space required for a given table using a formula. It basically involves the estimated raw size of your data for that table, multiplied by the key space's replication factor, and then multiplied by a factor related to your chosen compaction strategy, because compaction requires temporary space.
Okay, so you account for replication and overhead.
Exactly. Sum that up across all your tables. As for a rule of thumb for node size, historically, Cassandra operators often recommended aiming for a maximum of maybe 1 TB of actual user data per node.
Why that limit?
It's really about balancing storage density and cost against operational concerns. Nodes that are too large can take a very long time to perform operations like bootstrapping, decommissioning, or recovering after a failure, streaming data. So keeping nodes to a somewhat manageable size, like 1 TB or maybe 2 TB with modern hardware, often leads to a more operationally flexible cluster. But it depends heavily on the hardware and workload.
And what about other hardware considerations? Spinning disks versus SSDs, RAID or no RAID?
If you're forced to use spinning disks, HDDs, the strong recommendation is to use separate physical disks for the data directories and the commit log directory. The commit log benefits hugely from the sequential write performance of a dedicated disk.
And with SSDs?
With SSDs, it's generally fine to put both data and commit logs on the same drive because SSDs have excellent random write performance, which the commit log needs. As for RAID, for your data disks, you typically want either JBOD, just a bunch of disks, or maybe RAID 0 striping.
No redundancy like RAID 1 or RAID 5.
Generally, no. Cassandra handles data redundancy itself through its replication factor across different nodes. Using RAID levels that provide disk-level redundancy just adds unnecessary overhead and cost. You rely on Cassandra's distributed replication for fault tolerance, not local disk redundancy. And definitely be cautious with shared storage like SAN or NAS. They can introduce performance bottlenecks and single points of failure that negate Cassandra's distributed design. Direct attached storage is preferred.
Makes sense. And the network obviously must be critical in a distributed system like this. Any specific recommendations?
Critically important, yes. You need robust, low latency, high bandwidth networking between your Cassandra nodes. Think 1 Gbps Ethernet as a minimum, often 10 Gbps or higher in modern deployments. Correct firewall rules need to be in place to allow internode communication, typically port 7007-001, and client connections, typically port 9042.
Any benefit to separating traffic?
Yes, it's often a good practice, if feasible, to use separate network interfaces, NICs, for the internode, gossip, and data streaming traffic versus the client-to-node CQL traffic. This can help prevent high client load from impacting the essential cluster communication, like having dedicated lanes on a highway.
Okay, so the cluster is deployed, configured, networked, and now you have to keep it running smoothly.
Yeah.
How do you monitor its health and performance? What are the standard tools or interfaces?
Cassandra exposes a ton of management and performance data via JMX, the Java Management Extensions. JMX is a standard Java technology for managing and monitoring applications.
How do you access that?
You can use standard JMX clients like JConsole or Visual VM, which often come with the JDK, or more advanced tools like Java Mission Control, or integrate with larger monitoring systems that understand JMX. Through JMX, you can inspect specific mbeans, managed beans, that represent different components of Cassandra.
What kind of info can you get from mbeans?
All sorts. For example, the column family store bean, the name is historical, think table bean, gives you details about specific tables, storage size, SSTable counts, read-write latency statistics, cache hit rates, estimated number of keys, and more. The storage service mbean provides cluster-wide information, node status, gossip state, streaming operations, etc. JMX is really the fire hose of metrics.
Okay, JMX for deep metrics. But what about quick checks or common operational tasks from the command line?
For that, the primary tool is Node Tool. It's a command line utility found in the Cassandra home bin directory, and it's the operator's best friend.
What are the essential node tool commands someone should know?
Oh, several. Node Tool status gives you a quick overview of the cluster state, which nodes are up, UN up normal, or down, DN down normal. Their load, token ownership, data center, rack. It's the first thing you run if you suspect trouble.
What else?
Node Tool TP stats, thread pool stats, is incredibly useful for diagnosing performance issues. It shows you the status of various internal thread pools, active tasks, pending tasks, completed tasks, and crucially, dropped messages. If you see dropped messages, it's a clear sign that the node is overloaded.
Okay, status, TP stats. Anything for table performance?
Yes, Node Tool Table Histograms gives you detailed latency histograms for reads and writes per table, showing you the distribution, percentiles like P50, P99, P99, of how long requests are taking. Node Tool Proxy Histograms does the same, but for latencies measured at the coordinator level. And commands like Node Tool Info, Node Tool Ring, Node Tool Describe Cluster give you other general information about the node and the cluster topology.
I think you mentioned earlier, in Cassandra 4.0 plus Quartzine, there's another way to get some of this info using CQL. Virtual tables.
Yes, that's a great addition in 4.0. Cassandra now exposes a lot of internal metrics and configuration information through special non-physical virtual tables in key spaces like system views and system virtual schema. You can query these tables using standard CQL, which is really convenient for scripting or integrating with tools that already speak CQL. In fact, CQL itself now uses these virtual tables for some of its output.
What about logs? Where should you look if something goes wrong?
Standard logging is crucial, of course. The configuration is in conflogback.xml. The main log file you'll usually look at is system.log, which records general events, warnings, errors, and node lifecycle information. There's also debug.log if you enable more verbose logging, but be careful as it can grow very large.
Yeah, and 4.0 added some more advanced logging too.
Yes, two significant additions. First, full query logging, FQL, lets you capture the exact CQL query strings being executed by clients. This is incredibly useful for debugging application issues, security analysis, or capturing live traffic for replay in a test environment. You access these logs using a separate tool called FQL tool.
And the second one?
Audit logging. This is primarily for security compliance. It allows you to track specific categories of operations: mutations, DML, reads, schema changes, DDL, permission changes, DCL, authentication attempts, AUT, and errors. It has a pluggable backend, ARUG, file audit logger, bind audit logger, and is highly configurable to log exactly what you need for your security requirements.
Okay, monitoring and logging covered. Now, with all this replication happening, data consistency across replicas isn't guaranteed automatically over time, right? Nodes go down, networks partition.
Yeah.
How do you keep the replicas in sync?
That's right. While Cassandra's consistency levels handle consistency during read and write operations, entropy can creep in over time due to failures. To counteract this, you need to run repair operations periodically.
Repair, what does that involve?
The node tool repair command triggers a process where nodes compare their data with other replicas for the token ranges they own and stream any differences to bring everything back into sync. It's essentially an anti-entropy mechanism.
Are there different kinds of repair?
Yes. There's full repair, which compares all data in the owned ranges. Since Cassandra 2.1, there's also incremental repair, which is generally preferred. It only repairs data that hasn't been repaired since the last time SS tables were created or compacted, making it much more efficient for ongoing maintenance. You can also run repair sequentially, node by node, or in parallel across nodes, faster, but puts more load on the cluster.
How often should you run repair?
The general best practice is to run repair regularly, typically at least once every jet gray seconds period, which defaults to 10 days, to ensure deleted data gets properly reconciled before tombstones might be garbage collected. Many operators run it more frequently, perhaps daily or weekly, often using automation tools. It's important to schedule repairs carefully to avoid running conflicting repair sessions on the same nodes simultaneously.
And what about routine cluster changes, like adding or removing nodes or backups? Are those handled by Node Tool too?
Yes, Node Tool handles those basic lifecycle operations. Node Tool Bootstrap is implicitly run when a new node starts, if auto bootstrap is true. Node Tool Rebuild can stream data from other replicas to a specific node. Node Tool Decommission gracefully removes a node from the cluster, streaming its data to other nodes first. Node Tool Remove Node forcibly removes a dead node's ID from the ring.
And backups?
For backups, Node Tool Snapshot creates a hard link-based snapshot of all the SS tables for specified key spaces or tables. This gives you a point-in-time consistent backup on each node. You can also enable incremental backups, incrementalbackups.true in Cassandra.yaml, which creates hard links to new SS table files whenever a men table is flushed. You'd then typically combine these snapshots, full or incremental, with a strategy to copy them off to external storage. Differential backups are also possible by comparing snapshots.
It sounds like there's a lot of potential manual work involved in managing a large cluster, repairs, backups, scaling. Are there tools to help automate this?
Absolutely. For larger or more critical deployments, relying solely on manual node tool commands isn't really feasible or scalable. There's a growing ecosystem of tools for automated management and maintenance.
Like what?
Well, Netflix famously open-sourced Priam, which helps manage Cassandra clusters on AWS, handling things like deployment, configuration, backup restore to S3, and token management. DataStax offers OpsCenter, a web-based visual management and monitoring tool for their enterprise version, DSE, and now for Apache Cassandra too.
Anything more recent?
Yes, there's a move towards Cassandra sidecars running a separate management agent process alongside each Cassandra node that exposes REST APIs for common operations. This makes automation easier and decouples management from the Cassandra process itself. And in the Kubernetes world, Kubernetes operators like Cassandra, from data stacks but open source, are becoming very popular. They automate complex operational tasks like scaling, upgrades, repairs, and backups within a Kubernetes environment, treating Cassandra more like a cloud-native service.
Okay, let's shift to performance tuning. It's obviously not just about throwing hardware at the problem or running repairs. What are the key considerations when you're trying to squeeze every last drop of performance out of Cassandra?
Yeah, performance tuning is a deep topic in itself. The very first step, though, is always to define clear performance goals. What are you trying to optimize? Is it raw throughput, operations per second? Is it read latency, write latency, tail latency, P99, P999? You need specific targets.
And understand the trade-offs.
Exactly. Performance tuning is almost always about making trade-offs. For example, enabling compression on S-enables saves disk space and potentially network bandwidth, but it costs CPU cycles to compress and decompress data. Throttling compaction might improve foreground latency, but lead to more SS stables and slower reads later. Increasing the JVM heap size might reduce GC frequency, but lead to longer GC pauses when they do occur. Raising the consistency level improves accuracy, but typically reduces throughput and increases latency. It's a constant balancing act based on your goals.
So once you have goals, how do you test if you're meeting them? Is there a standard load testing tool?
Yes, the tool that ships with Cassandra itself, called Cassandra Stress, is really powerful for this. You can use it to simulate various workload patterns, reads, writes, mixed, configure consistency levels, concurrency, data sizes, and really hammer your cluster under both nominal and peak conditions to see how it holds up against your performance goals. It's essential for benchmarking and testing tuning changes.
And for analyzing the results, we mentioned node tool, TP stats, and table histograms. Anything else?
Those node tool commands are key for identifying bottlenecks on the nodes themselves. JMX metrics provide even deeper insight. For visualization and long-term trending, integrating Cassandra's metrics, often via JMX exporters, into monitoring systems like Prometheus and then visualizing them with dashboards in Grafana is a very common and powerful setup. It lets you see performance trends over time and correlate issues.
What if you're trying to debug a specific slow query? Is there a way to see exactly what's happening for just one request?
Yes, that's where tracing comes in. You can enable tracing for individual queries, either by typing tracing on in cpelch before running your query, or by enabling tracing programmatically using the driver. Set tracing true.
What does tracing show you?
It provides incredibly detailed microsecond level information about the entire life cycle of that query execution. You'll see the request hitting the coordinator sending requests to replicas, reads from mem tables, reads from specific SS tables on replicas, data merging, and the response coming back. It breaks down where every millisecond is being spent, including internode communication. It's invaluable for pinpointing why a particular query is slow. Maybe it's hitting too many SS tables, waiting on a slow replica, or indicating a data modeling issue.
That sounds powerful. Does it impact performance?
Enabling tracing does add some overhead, so you wouldn't leave it on all the time for all requests in production. Also, the trace data itself is stored temporarily in a Cassandra table, systemtraces.sessions, with a short default TTL, like 24 hours, to prevent it from filling up your disk.
And this tracing concept, it fits into broader industry ideas too.
Yes, absolutely. Cassandra's per-query tracing fits perfectly into the larger concept of distributed tracing, pioneered by systems like Google's Dapper paper and implemented by open-source frameworks like Jaeger and Zipkin. You can often integrate Cassandra trace IDs with trace IDs from your application services, giving you an end-to-end view of a request as it flows through your entire microservices architecture, not just within the database layer.
Okay, so tracing for specifics. What are some of the actual knobs you can turn in Cassandra for general performance pinning? What areas can you adjust?
There are quite a few areas. Caching is a big one. Cassandra has several caches. The key cache maps partition keys to row index entries in memory. The row cache can store entire frequently accessed rows, but use with caution as it can cause GC pressure. The off-heap chunk cache stores uncompressed SS-stable data chunks. And the counter cache optimizes counter updates. Tuning the sizes of these caches via cassandra.yaml can significantly impact read performance, trading memory for reduced disk I/O. Node tool commands let you inspect cache hit rates and manage them.
Wells.
Memtable settings control how much data is buffered in memory before being flushed to S-tables. Tuning memtable flush writers and related settings can impact write performance and flush behavior. For SS tables, besides choosing the right disk type, SSD is strongly preferred, you can tune file cache anim, if using the OS page cache, and compression options, like algorithm LZ4 is the default and usually a good balance and chunk length theme.
What about concurrency in the JVM?
You can tune concurrency settings like concurrent threads, concurrent writes, and concurrent counter writes to adjust how many requests the node tries to handle in parallel, balancing throughput against resource usage. JVM settings are absolutely critical. Tuning the heap size, XMs, XXMX, and JVM.options is vital historically. With older garbage collectors like CMS, you'd often cap the heap at around 8 GB to keep GC pauses manageable, but with newer GCs like G1GC, often the default now, or experimental ones like Shenandoah or ZGC, larger heaps might be feasible. Choosing and tuning the garbage collector itself is a major performance lever.
And can you tune things from the client side too?
Yes, client-side tuning is important as well. Using prepared statements is almost always recommended for performance. Drivers often have a request tracker feature to log slow queries from the client's perspective. Enabling client-side request tracing can help debug issues, and some drivers offer request throttling mechanisms to prevent a misbehaving client application from overwhelming the cluster with too many concurrent requests.
Wow, lots of levers to pull. Okay, let's quickly touch on security before we wrap up integration. What are Cassandra's main security features for protecting your data? How do you lock it down?
Cassandra provides security features across 4 main pillars. Authentication, who are you? Authorization, what are you allowed to do? Encryption, protecting data on the wire and optionally at rest. And audit logging, tracking who did what.
Okay, starting with authentication. How do users or applications prove who they are?
You need to enable an authenticator in Cassandra.yaml. The most common one is the password authenticator, which stores usernames and hashed passwords internally in Cassandra's systemeth keyspace.
How do clients provide credentials?
The client drivers provide ways to supply the username and password when establishing a connection. For example, the DataStax Java driver has methods like withauth credentials. Once authentication is enabled, anonymous connections are typically rejected.
All right, so you're authenticated. Then comes authorization. What can you actually do?
Cassandra uses a role-based access control RBAC model for authorization. You need to enable an authorizer, typically the Cassandra authorizer, in Cassandra.yaml. Then you use CQL commands like create role, grant, and revoke to manage permissions.
Roles, not users.
Interestingly, Cassandra uses the concept of roles for both individual users and groups of permissions. You can create roles that represent users and potentially grant login to them, and other roles that represent sets of permissions, for example, read-only role. You can then grant roles to other roles, creating hierarchies. Permissions themselves are things like select, modify, which covers insert, update, delete, create, alter, drop, authorize, etc., and they can be granted on specific key spaces or tables.
Okay, authn and authz covered. What about protecting data in transit? Encryption.
Yes, securing data on the wire is crucial. Cassandra supports SSL/TLS encryption for both node-to-node internode communication and client-to-node communication.
How do you set that up? Is it complicated?
It involves a few steps. First, you need to generate SSL certificates, typically a key pair for each node and potentially for clients. For development clusters, you can use Java's key tool utility to generate self-signed certificates, export public keys, and create key stores and trust stores. JKS format was common for dev, but PKCS12 is often preferred now. For production, you'd usually use certificates signed by a trusted certificate authority, CA.
Then you configure Cassandra.
Yes, in Cassandra.yaml, you configure the server encryption options section for node-to-node encryption, providing paths to the key store and trust store files and their passwords, and setting options like internode encryption to all or DC. Similarly, you configure client encryption options to enable and require encryption for client connections, again specifying key store trust store details. Once enabled, communication happens over secure encrypted tunnels.
What about securing remote management access like JMX? Is that encrypted by default?
JMX is typically not secured by default and often only listens locally. For secure remote JMX access, you need to explicitly configure it. This usually involves disabling local JMX and setting specific JVM properties in the cassandra-nv.sh or jvm.options file to enable JMX authentication using a password file, and optionally JMX SSL using certificates. It's an important step if you need remote JMX management.
And finally, audit logging, we mentioned that earlier. How does that fit into the security picture?
Right. Audit logging, especially the features added in 4.0, is the 4th pillar. It provides an immutable record of who performed critical actions, which is essential for security compliance and forensic analysis. By configuring the audit log manager in Cassandra.yaml and enabling specific categories, query, DML, DCL, and the error, you can track exactly who is accessing or modifying data, changing schemas, or logging in out, providing that crucial accountability trail.
Okay, comprehensive security. So we've designed our application, deployed Cassandra, We know how to operate it, monitor it, tune it, secure it. Now let's talk about integration and migration. How do you adapt existing applications or integrate Cassandra into a larger data ecosystem?
Adapting your application code is often the first step. You really need to embrace Cassandra's data modeling principles. That means thinking about denormalization and using batches, perhaps, to keep multiple denormalized tables in sync after a single logical update.
And using lightweight transactions for those special cases.
Exactly. Using LWTs, if not exists, or a hive condition, when you need to enforce uniqueness or perform atomic check and set operations, like ensuring a flight reservation confirmation number is truly unique before finalizing the booking.
What about putting logic inside Cassandra? You mentioned user-defined functions, UDFs, and
Yeah.
aggregates, UDAs, earlier. How do they fit into integration?
They can be powerful tools for certain kinds of processing. User-defined functions, UDFs, allow you to write custom functions, typically in Java or JavaScript, that get executed directly on the Cassandra nodes as part of query processing.
Like what kind of function?
Maybe a function to parse a complex data type stored in a column or perform a specific calculation. For instance, in our hotel example, maybe a UDF count if true applied to a list of booleans representing room availability for different dates. You need to enable UDFs in Cassandra.yaml, they run in a security sandbox, and then use create function in CQL.
And user-defined aggregates, UDAs.
UDAs build on UDFs. They allow you to perform aggregate operations across multiple rows returned by a query, similar to SQL's SUM, AVG, count, etc. But you define the aggregation logic yourself. They use a state function, a UDF, that updates an intermediate state for each row, and optionally a final function to produce the result. For example, you could create a UDA total available that uses UDF to sum up the number of available rooms across multiple rows returned for a specific hotel query. They let you push some aggregation logic down to the server side.
Okay, interesting. Now, for migration, if you're moving data from an existing system, say your relational database, into Cassandra, what are the strategies? Especially if you need to do it with minimal or zero downtime. That sounds challenging.
It can be, yes. A very common approach for achieving zero downtime migration is often called the dual write technique.
Dual write.
Yeah, you modify your application so that for a period of time, it writes data simultaneously to both your old database and your new Cassandra cluster. While the dual writes are happening, you perform an initial bulk load of all the historical data from the old system into Cassandra.
What tools do you use for that bulk load?
There are specialized tools designed for efficient bulk loading into Cassandra. dsBulk from DataStax is a popular command line tool optimized for high-speed loading and unloading of data, CSV, JSON. Apache Spark, using the Spark Cassandra connector, is also very commonly used, especially for more complex ETL, extract, transform, load processes during migration. Spark can read from various sources and write efficiently to Cassandra in parallel.
And once the bulk load is done and dual writes are running, how do you ensure the data actually got migrated correctly? Validation seems critical.
Absolutely critical. You need a solid data validation strategy. dsBulk provides detailed logging, including logging rows that failed to load. For more comprehensive validation, you might write custom Spark jobs to read data from both the source and target Cassandra databases and compare them, looking for discrepancies. There are also some open source projects, like the Cassandra Diff tool, designed specifically to compare data between two Cassandra clusters, which could be adapted or used for inspiration. Thorough validation gives you confidence before you finally cut over reads to the new system and turn off the old one.
Okay, migration strategies covered. Lastly, what are some of the most common integrations for Cassandra? What other pieces of a modern data architecture does it often work closely with?
Cassandra fits really well into modern, often event-driven architectures. One of the most common and powerful integrations is with Apache Kafka.
Kafka for event streaming.
Exactly. A typical pattern is for an application service to write an event, like a new order or a hotel reservation, to a Kafka topic. Then, other downstream services can consume that event from Kafka and update their own state, potentially stored in Cassandra. For example, a reservation service writes to Kafka, and an inventory service and an email notification service both consume that event to update Cassandra tables and send an email.
Can you stream data directly between Kafka and Cassandra?
Yes, Kafka Connect is Kafka's framework for streaming data between Kafka and other systems. There are connectors available, like the DataStax Apache Kafka connector, specifically designed to efficiently stream data from Kafka topics into Cassandra tables.
What about getting data out of Cassandra? For example, if changes in Cassandra need to trigger downstream actions.
For that, Cassandra has a feature called Change Data Capture, or CDC, which became production ready around version 3.8. When enabled on a table, Cassandra writes mutations, inserts, updates, deletes for that table to special commit log files. Downstream systems or agents can then consume these CDC logs to react to changes happening in Cassandra in near real time. It allows Cassandra to be a source of events for other systems.
And what about analytics? Can you run complex analytical queries directly on Cassandra? We know it's optimized for key-based lookups.
While Cassandra itself isn't primarily an analytical database, direct full table scans are discouraged, it integrates extremely well with Apache Spark for analytical workloads.
How does that integration work?
The Spark Cassandra connector allows Spark jobs to read data from Cassandra tables into Spark data frames or RDDs and write data back out. The key benefit is that Spark can execute complex analytical queries, aggregations, joins across different tables, machine learning tasks, over the entire dataset in Cassandra, bypassing CQL's query limitations.
Does it help to run Spark on the same nodes as Cassandra?
Yes, often. Co-locating Spark worker processes on the same nodes as Cassandra data nodes allows Spark to read data locally, minimizing network transfer and maximizing performance for analytics. The connector is aware of Cassandra's topology and tries to schedule Spark tasks close to the data they need. This makes Spark a very popular choice for running batch analytics or even complex ad hoc queries against large Cassandra datasets.
Wow, okay. We have covered a tremendous amount of ground today. From understanding why traditional relational databases really hit a wall at web scale
Yeah, those bottlenecks.
to diving really deep into Cassandra's distributed architecture, its focus on availability, that whole concept of tunable consistency, and its flexible data model.
We got into the nitty-gritty too: commit logs, SS stables, tombstones, compaction.
Absolutely. And then the practical side, operational tools like Node Tool and JAMX,
Mm-hmm.
monitoring, security considerations, and how to integrate Cassandra with other key parts of the modern data stack like Kafka and Spark.
It really paints a picture, I think, of how Cassandra tackles those modern data challenges. It offers storage that's fundamentally distributed, designed for high availability, and gives you that control over consistency. Its flexible model and the whole ecosystem around it really do support these complex, high-demand applications, directly addressing those shortcomings we saw with traditional RDBMS at true web scale.
Definitely. It's clear why it became such a foundational piece for so many large-scale systems.
Mhm.
So for everyone listening, hopefully this deep dive has equipped you with the key concepts and practical insights to understand why Cassandra is so vital, how you might get started with it, and what's involved in managing and optimizing it.
Yeah, hopefully it demystified it a bit.
Mm. And with that, we'll leave you with this final provocative thought to chew on. In a world where data is constantly growing, seemingly exponentially, and applications demand ever-increasing availability and responsiveness, what kinds of new insights or new capabilities might become possible if we truly embrace the idea that data storage doesn't have to be the bottleneck, but could actually be an enabler for future innovation?